Now that we know that the zero of the derivative function will give maximums and minimums for the function itself, we can examine certain aspects of the two functions, and we can actually determine algebraically whether or not we have a maximum or a minimum at any particular critical point. That is, at any particular point where we do have a zero of the derivative function. Let's look, though, before we look at the algebra of it, look at the geometry of it, or the graphs. Here we have a function, and we know that at this point, at this relative maximum point, and it's relatively a maximum because it's not the absolute maximum. There are maximums or values of f of x that are larger than this one over here. But in this neighborhood, this is a maximum point. Okay. So we have a relative maximum here, and we know because of that f prime of this point, of this x, f prime of that x is going to be 0. We have here a relative minimum, and f prime of that x is also going to be 0. Now, let's examine what happens in intervals around these critical points, we'll call them. All right, in the interval to the left of this maximum, notice what's happening to the function. The function is rising. It's increasing on the interval from negative infinity to here at negative 2. So we have the function is increasing. Now, think about what's happening with the slope of the tangent line during this period of increasing time. We have an increasing function, and so the tangent line is positive during this term, or during this time. And then after the critical point, we have a declining graph, we have a decreasing graph, and so in this interval of decrease, we have a tangent line whose slope is negative. So we have a negative values of f prime in this neighborhood, and then as we go over to the increasing graph again, we have positive tangent line slopes, and therefore we have positiveness in the f prime, in the graph of f prime. All right, look at f prime. Now here's f prime, here's f. Okay, we know that the max and mins will give zeros for the f prime graph. All right, we know that on this increasing part of f, the slope of the tangent line is positive for all of these, so we're above, you see, the x-axis here for the graph of f prime. During this interval, or in this interval of f, we have a declining graph, we have tangent lines that are negative, or the slopes are negative in this area, and therefore all of the values you see within in this interval on f prime are below the x-axis. They're negative. So f of all of these x's down here, f of the x's in this interval are all negative. Slope of the tangent line is negative in this interval. That's the idea. And then when we go back to the notion of an increasing graph, positive slopes, we have positive values for our derivative function. All right, that's what it's all about graphically. And these two really play in a little dance together, don't they? Well, let's think about what it means for a graph to be increasing or decreasing. It means this, that if we have an increasing situation, it means that given a couple of points x1 and x2, as long as x1 is less than x2 along a particular interval, x1 is less than x2, this implies that f of x1 is below less than f of x2. You see, come back over to the graph. x1 is less than x2. Let's see, we're at an increasing situation. We're kind of defining it algebraically, and here we're increasing along this interval. Think about, along this interval, if I choose an x1 that's to the left of an x2, smaller than an x2, f of x1 is smaller than or below f of x2. That's what that says. Now, the decreasing idea is very similar, that along a particular interval, we have a decreasing interval if for every x1 that's less than x2, this implies that f of x1 is above or greater than f of x2. Let's look at it graphically. x1, here we have a decreasing interval. In this interval, we're decreasing. Okay, now in that interval, we have an x1 that's less than an x2. Now that means that f of x1 is greater than the f of x2. You see, this one is above that one. And that's the nature of increasing and decreasing symbolically. Now, to summarize the idea on the f prime function in a particular interval a, b, as long as f prime of x is greater than 0, f is increasing. Now let's say it again. As long as f prime of x is greater than 0. Well, where is f prime of x greater than 0? That is above the x-axis. In this interval, f prime of x is above the x-axis. F prime of x is greater than 0 on this interval, and sure enough, on the same interval, the graph of f is increasing. All right, when f prime of x is less than 0, it implies that f is decreasing. In that interval a to b, where f prime of x is less than 0, where is that on this graph? Well, it's in this interval. You see, f prime of x is below the x-axis, so f prime of x is less than 0, and in that same interval, we have a decreasing graph on f. And if we have places or regions, intervals along the f prime graph where it's equal to 0, then f is constant. Now, that doesn't happen over here. We don't have a region on f where we have a constant graph or a kind of a flat graph. That's what would happen if we had a flat graph. Then we would have f prime of x would be 0 for an entire interval. Well, consider the function that defines that graph over there. Here's that function. All right, here's the f of x that makes that graph over there. Now I've changed x cubed over 4 to 1/4 x cubed in order to accommodate the derivative function. F prime of x then is, let's see, 3 times 1/4 x squared, and then minus 3. Now I want to find the 0. I want to find the 0 of, or the zeros of this expression in order to identify what we call critical points. The points where the graph of f may change from increasing to decreasing, you see, and the points where we may have relative maximums or minimums. Okay, so that's what we're after here algebraically. We're going for these critical positions in the graph to make an examination using our functions. All right, so f prime of x is this. We're looking for zeros, so we want to solve this. We go through a little simplification and a factorization. The zeros are at the values of x that will cause the factors to become 0. This factor is 0 when x is -2. This factor is 0 when x is 2. So our critical numbers then would be x equals -2 or x equals 2. Now also critical numbers are places where the f prime function turns out to be undefined. We don't have that situation here, but that is the case as well. Now, we form intervals. Here are critical numbers. Now, our intervals that we form are the intervals that are around these critical numbers. To the left of that critical number, to the right of that critical number, and between these two, and then to the right of this critical number. If you think of these numbers on a number line, you see, you just take these numbers and divide that number line according to those positions, and then you want the intervals that these critical numbers break the number line into. So the intervals would be, let's see, if x is -2 is a critical number, then one test interval would be from -infinity to -2. And the next interval would be from -2 to 2. And then the next test interval would be from 2 to infinity. So 2 to infinity. Now what's happening in those intervals? Let's examine what's happening. So we want to evaluate f prime of x within that interval. So in this interval, how is f prime behaving? Is it positive or negative? That's all we're after. That's all we need to know. So we'll just take a value. You can take a value in the interval and put into the f prime function. For example, if we're thinking about entries or x values in this interval. We can choose an x that is less than -2. Any x will do. -10, for example, would do fine. Something like that. We come over here to the f prime function. We would put in -10 squared. That's, that's 100. 100, 3/4 of 100, that's 75. Minus 3, that's still positive. And all we're doing is identifying positiveness or negativeness. So f prime of x would be greater than 0 in this interval. And that means if the derivative function is positive in an interval, that means that the original function is increasing in that interval. And in a similar way, we evaluate x's that fall into this interval. We find that f prime of those x's would turn out to be less than 0. And if the f prime is less than 0 in an interval, it means that the function itself is decreasing. Then we go over to the next interval and perform the same kind of test or the same kind of evaluation. For these values of x, f prime turns out to be positive. And if it is, then f is increasing. Now, think about the notion that we're sort of going left to right on our coordinate plane from in this interval and then the next interval and the next interval. Now, if f is increasing on this interval and then f is decreasing on this interval, it should make some sense that there is a relative maximum, you see, at our critical point dividing those intervals. And that turns out to be the case. So we can say that there is a relative max at where's the dividing of this? Well, this interval goes up to -2. This one starts at -2. So there is a relative max at x equals -2. And then if f is decreasing in this interval and then increasing in that interval, you see there must be a relative minimum right at the critical point dividing these two intervals, and that turns out to be the case. So we would say that there is a relative min at, at x equals 2. Now, that brings us to the summary of all of this is the first derivative test. And the first derivative test is very simple. I mean, it's almost obvious from what we've been talking about. It simply says this, that if f prime of c changes from positive to negative at c, you see, if the derivative function changes from positive to negative, from positive, you see, positive to negative at c, then c is a relative maximum. If f prime of c changes from negative to positive, from negative to positive at c, then c is a relative minimum. Kind of an obvious consequence from what we've been talking about. Let's use the first derivative test on this function to see if we can identify relative max and min points. Here's our function. We first of all take the first derivative, and it turns out to be 4x cubed minus 6x squared. Now we want the zeros as our critical points. Factoring, we get 2x squared times 2x minus 3. The value of x that causes this factor to become 0 would be 0. The value of x causing this factor to become 0 would be 3/2, 3 over 2. So our critical numbers are x equals 0 and x equals 3 over 2. These actually now are candidates as points where we may have a relative maximum or minimum point. We want to know whether we do or not. We want to know whether it's a maximum or a minimum. All right, here's how we tell. Now, these 2 points are subdividing our x-axis. We could think of it like that, subdividing the x-axis into intervals. The interval from -infinity to 0, the interval between these two, and the interval from 3 over 2 to infinity. So I've written those intervals up here from -infinity to 0, 0 to 3 over 2, 3 over 2 to infinity. And then we want to evaluate the behavior of f prime of x. And to do that, we take a value in the interval. Now here we can take any negative number that we care to. And suppose we take -10, for example. So we would come back over here and evaluate f prime of -10. And if we put negative 10 here, negative 10 cubed is negative 1,000 times 4, negative 4,000. You see, and that'll overwhelm this term, so the value, the function is negative in that interval. So f prime of x is less than 0 in that interval. Now, let's go through the evaluation process here, and then we'll come down on this kind of chart layout in just a moment. So let's see f prime of x in this interval. Now, between 0 and 3 over 2, which is 1.5, 1 appears. So let's evaluate for f prime of 1. So we'd come back over here, and we'd pop in a 1 here and here. So we have 4 minus 6, negative 2. So f prime of 1 is negative, and so the function is negative in the interval. Now notice that f prime of x is less than 0 in both of these intervals. All right, that's kind of an interesting thing. We wouldn't expect that. We expected there to be a difference as we go along, or that has been the case in the past. At any rate, f prime of x in this interval, we just take a very large number. We find out that f prime of x is positive in this interval. Okay, now what does that mean? Well, it means that the function itself is decreasing. If we're talking about an f prime of x that's less than 0, slope of the tangent line is negative. We can think of it as slope of the tangent line is negative. You see falling from left to right. So the function is decreasing. Now here the function is decreasing as well. So we don't have a relative minimum as we might have expected along this interval. We might examine the situation and see what we do have at that particular critical number. But at any rate, we don't have a minimum, but from this decreasing to increasing idea, so the function is decreasing here, and then the function is increasing over in this interval. So at the critical number, we have a relative minimum. So we say we have a relative minimum at x equals 3 over 2. Let's take a look at the graph of this on the graphing calculator. Here's a graph of the function. We know from experience that the zeros of the derivative function will often give maximum and minimum points on the original function. Well, the zeros of the derivative function were at 0 and 3 over 2. And the 0 critical point did not give us a maximum or minimum point on the original function. And this is why. It's the function in the interval from negative infinity to 0, the function is decreasing, but then it's decreasing again, you see, along this next interval from 0 to 3 over 2. So it kind of flattens out right here, but we don't have a relative maximum or minimum. Let's take a look at the derivative function. I have already entered it here, and now I simply want to select it. And I'm pressing F5 to select it, and it's highlighted now. The equal sign is highlighted. And I'll go to the graphing. And I'm graphing it in a different kind of pattern, in a thick line here. Now, notice that throughout the interval from negative infinity to actually to 3 over 2, that the derivative function is negative throughout this region. And that's kind of important because our first derivative test is telling us that we have a minimum or maximum when we change from negative to positive or positive to negative. And at this point, we're going from negative to positive, and therefore we have a relative minimum.